Hi guys. Okay, welcome to my channel. So today we are going to move on to something new, still on vector calculus. And what we're going to be studying today are what are known as space caves. So these are some special vector functions that have some physical meaning behind them. So that's what is going to be our main focus today. So the things that we are going to discuss in this lesson, first we shall provide a definition of space caves. Then the next thing that we're going to do, we're going to look at what are known as regular or smooth space caves. Then the next thing, after talking about regular or smooth space caves, we are going to look at the what is called the unit tangent vector. Then finally we'll look at finding equation of the line of tangency. Of a space cave. So yeah, these are the few things that we want to look at in today's lesson and try to understand also the type of problems that one will come across and see how we get to solve such problems, you see. Okay, so to begin now, let's look at the definition of a space cave. So what exactly is a space cave? So a space cave is a vector function that represents a cave in space. You see that? So this is a vector function that represents a cave in space and has the form, and this vector function has the form r of t equal to xt yt z of t. So this is what we call a space cave, and the parameter t should always be defined in such a way that it takes values that lie within a certain interval, where this I represents some interval that has been chosen, like that, you see. So when we talk about space cave, that's exactly what a space cave is. It's just a vector function. It's a parametric vector function. As you can see, it still takes the structure of the vector functions that we've encountered before, which are parameterized in terms of parameter t. But the only difference now is that this one is a physical meaning behind it. So these are caves that represent trajectories of things that are moving in space. So that's why we had to separate their study from the rest, because they are going to also bring about some concepts that are also tied to things that are moving, as you are going to see during this discussion, you see. So that's what a space cave really is. So an example of a typical one in space will be something like this. So how it will look in space, it will be something like this, where you have your x, y, z. So a space cave is just a cave which goes randomly in space and flows, you see. So what we refer to as the r of t is then a line which starts from the origin and is attached to some point along that curve. So that's what the vector r of t really is when we are to draw it in space. So this is exactly what we mean when we talk about a space curve. You see, so that's exactly what we mean. So when we say a vector function represents a space curve, it means it just represents a curve like this one that may be a trajectory of a moving particle in space, or anything that is just undergoing motion in space. So that's what these objects are. So now we have defined what a space curve is. So the next thing that we want to discuss now is that since these objects they are more tied to motion of moving things, you will see that we always require things that are moving to move smoothly. You see that without coming to stop or breakdowns or things like that. So you will see that the type of vector functions or space curve that we are going to be looking at in the whole of this section will be the ones that have what we call a smooth property, or ones that are smooth. So let's understand first what do we mean when we say something is smooth or a regular space curve. You see that? So smooth or regular space curve. So let's discuss now. You see? So a space curve. So a space curve R of t with t belonging to some interval, which I'll just define now as some interval AB, is said to be smooth or regular in AB if the derivative of the space curve is not equal to 0 for all t elements of the given interval. You see? So that's what we mean when we say a space curve is smooth. You see that? It means they do not exist points when the derivative of the parametric function r of t can never equal to 0 for all t that lie within the given interval. So if this property holds true, then we say the space curve is smooth. You see that? So we can see definitely from this that there is already a result that one can just write immediately from this. So this implies the space curve is a function which is such that the absolute value, which is the magnitude of the gradient, must never equal to 0 for all t elements of AB, of the given interval. So that's what we mean when we say a space curve is regular. It means it has to satisfy this condition, and we don't care if this condition were to break for some parameter values that are outside the given interval. What we want is for the defined interval, this property must always hold true. The derivative must always be like this, and also, and r prime of t must be continuous in this interval. So also in the given interval, the function r prime of t again must be a continuous function in that specified interval. You see, so that's also what we need. Yes, we do not need the derivative to come to 0, but the other thing is it must be continuous for each and every point that lies within that given interval. So that's what we need. What needs to be satisfied for a space curve to be characterized as being smooth or a regular space curve. So let's see then some problems that one can encounter when it comes to the smoothness of space curve. So a typical example that you can get in exam is something like this. So they will say, given the space curve r of t, which is equals to 3 sine t, 4 cos 2t, 3t, with t element of real numbers, show that this curve is regular. So this is what you will get. You will get a problem like this one when you are given a space curve and you are asked to show that this thing is regular for all parameter values that lie within the space of real numbers. So how can we then solve a problem like this one? So to solve a problem like this one, already we have seen that if you want to prove the smoothness, you need the derivative of the space curve. So let's find this first. So what is r prime of t? So r prime of 3 is 3 cos t minus 8 sine 2t and 3, like this. You see. So what can we see here? It is easy. It can be seen already that r prime of t is continuous in R. So this is obvious. This is obvious. We can see that, yes. And also what do we see? And also one thing that we see is that the x coordinate of r prime of t, it can never be 0 for all t elements of real numbers. You see that? So the x component of the r function 3 can never equal to 0 because the z component, so it's the z component, sorry, not the x component, the z component. We can see that the z component of r prime t can never be 0 for all real numbers. So what conclusions can we make from that? So since this component can never be 0, it follows that r prime of t can never equal to 0, 0, 0 for all t elements of real numbers. And therefore, from this, it follows that RT is regular. You see. So this is how you get to tackle a problem. So every time when you are just proving that a curve is regular, you must just understand what is your main goal in such a problem. So every time the main goal of you is to convince someone that for any parameter that you can choose, it is impossible to get a parameter value for which all the components of this given derivative can be 0 at the same time. You see that? So once you can give a convincing argument that you cannot have all these components being 0 at the same time for all parameter values that lie within a specified range, then we have proven that the curve is smooth or regular. You see that? So let's see now another different example from this one asking the same thing. So another example that you can get is something like this. So given r prime of t, which is defined as 3 cos t sine 2t, 3 cos 2t, with t an element which ranges from minus pi over 4 to 7 pi over 6. You see, so show that r prime of t is regular. So how can we then solve this one? So we know that every time when you want to prove regularity, there are two things that you must show. One, it is the continuity of the function within the specified range or interval. So what we can do now is, let's see if that is the case by first finding the derivative. So let's differentiate to find r prime t. We can see that this is just negative 3 sine t, then 2 cos 2t, and then minus 6 sine 2t. So this is what we have now. You see that? So we can see that r prime t is continuous in the interval negative pi over 4, 7 pi over 6. So that's one thing that you can see immediately from that this derivative function is continuous because sine, cos functions, they are continuous functions. They are periodic, but they are continuous. That's all that matters. So now we have to prove now that it is impossible to have this derivative equal to 0 for some parameter value. So what I'm going to do now is I'll just take one of these components. You see that? So let's consider the x component of this derivative, which I'll denote as rxt, which is negative 3 sine t. And what do we know? We know that this component is 0 when what? So we know that this component can only be 0 under one case. It can only be 0 when t is a multiple of pi with n an integer. You see that? So sine can only be 0 for only integer multiples of pi. That's one thing that we know. So that's the only case where we can have the sine function vanishing. So what we're going to do now is we're going to see now that for this given interval, do we have any other integer multiple of pi that lies inside there? You see that? Do we have anything that lies inside there? So sometimes when you're solving this problem, it is good to always go back to degrees just to be aware of what exactly is the interval that we are dealing with. So this interval that you are dealing with, negative pi over 4 to 7 pi over 6, if you are to convert it to degrees, you will see actually it represents negative 45 degrees to 270 degrees. You see that? So this line, I write it in red because when you're solving this problem, you must not show something like this in your calculation. This is just to guide you into making sure that you are able to scoop all the t values that you require within the given interval. So we know already that sine can only vanish when you have an integer multiple of pi, which means the sine can only vanish when you have only an integer multiple of 180. So what I have to do now, we have to make sure that from this interval that is given, we extract all integer multiples of 180. But we can see that there is only two things that are like that. You see that? So in this case, sine t is equal to 0 for only t equals to 0 and t equals to pi. You see that? Because we can see that the only integer multiples of pi that we have in this interval are just 0 and pi. So which means this component can only be 0. So in this case, sine t can only be 0 for t equals to 0 and t equals to pi. You see that? Which is the case also for r prime zt. So if you look now, you will see that the z component of the derivative also is dependent on sine, which means for these two values that we have mentioned, which is 0 and pi, it's also going to vanish. You see that? But now let's check. You see that? But now what we have? Now let's evaluate the x component at this position. So what is the x component of the derivative when t is 0? So when t is 0, you will see that you place there, you get cos 0, which is 1, so you get 2. And again, if you find r prime of t, when t is equal to pi, what do we get again? So again, you go in and plug in, you will get 2 cos 2 pi. So you can use your calculator to punch this one and check. So let me punch it up and see what exactly do we get when we punch 2 cos 2 pi. So we get 2. again. You see, which is non-zero. You see that? So therefore, what do we see? We see that Rx of t is not equal to 0 for t equals to 0 and also for t equals to pi. Therefore, R prime of t is not equal to 0 for all t that lies in the given interval, which was negative pi over 4 to 7 pi over 6, and thus R of t is regular. You see, so this is how you solve problems where you have to prove the regularity of function or the smoothness of function. You just have to give convincing arguments that it's impossible to have all components vanishing at the same time. So we already saw here that the x and the y and the z components of this derivative, they both vanished at the same set of parameter points. But for those points where they were vanishing, the center function was not vanishing in this particular case, which means now we can see that they do not exist instances where you can have all these things vanishing at the same time. You see, so that's how you can prove that something is smooth. You see, but again, that's not the only way you can actually reason through problems. So let's look at also another different example. So another example that we have, it goes as follows. So given that R of t is equal to 2 cos t, 2 sine t, then t squared, with the t element of real numbers, show that R prime of t, R of t is regular or smooth. You see, so how can we show that R prime of t is regular or smooth? So to do that, this is how we proceed. You see, so first we find our derivative function, which is just going to be negative 2 sine t, 2 cos t, then 2t, like that. You see, so what do we see here? We see that it's clear that R prime of t is continuous for t elements of real numbers, because the sine is continuous, cos is continuous, and the polynomial is continuous again. So this is a continuous function in real numbers. But now, let's calculate now the modulus of this thing, or the size or the magnitude of this derivative function. So you will see that the absolute or the size of this derivative function will be negative 2 sine t squared plus 2 cos t squared plus 2t squared. So now let's simplify this and see what happens. So we get root. So here we'll have 4 sine squared t plus 4 cos squared t, then plus 4t squared. So if you check now, you will see that if you pull some 4 here, you will have sine squared t plus cos squared t plus 4t squared. But we know already that sine squared t plus cos squared t is 1, so we just get root of 4 to 1 plus t squared. Pull out the 4, you get 2 root of 1 plus t squared. So now what do we see here? What do we see here? So the question now that we should ask is there a possibility for this thing to be 0? You see that? Already from this, it's clear that root of 1 plus t squared is greater than 0, not even an equal to. So it's strictly greater than 0. for all t elements of real numbers. Therefore, this absolute value of RT is not equal to 0 for all t elements of real numbers. Therefore, R of t is regular on R. So you can see this is how we get to prove that space curves are regular. You see that? So we say a space curve is regular whenever this holds true. It's either you can prove that the derivative cannot be a zero vector for all parameter values that lie within a specified interval, or you can prove that we can't have the magnitude of that derivative function being equal to 0 for all parameter values. So this is how you get to solve these kind of problems every time when they are brought forward. Okay, now that we have seen, let's see again, what other things do we need to have every time? So most of the time when we are dealing with the space curve, since we want to tie everything to motion, there are some things also that we will prefer to have because in those instances, we know that whatever we're dealing with will be kind of like unique and it won't be shared by anything else. So that's why now you will see that one of the things that we are going to look at are what are known as simple space curves. You see, so most of the space curves that we want to look at, they are those that are simple. But what does it mean now to say a space curve is simple? You see that? So a space curve R prime of t with t an element of some interval ab is said to be simple, is said to be a simple space curve if R prime of what? So if R prime of x is not equal to R prime of y for all x and y elements of AB. You see that? So that's what we mean when we say a curve is simple. But what does all this mean? What does all this mean? So it simply means, i.e., a curve is simple when it doesn't intersect itself within the given interval. You see that? So we say a curve is simple whenever it doesn't intersect itself within a given interval. So what exactly do we mean by this? So what we mean by this is that we don't want situations like this where you have a space curve which is like this, where there's some intersection point. You see that? So we want just curves that go like this. So they start their motion somewhere and end it somewhere without getting to intersect each other like this. So every time when there is some intersection, then this is what we refer to as a non-simple curve. You see that? So what we have here is something which is not simple. And here is what we call when we say a function is a simple curve. You see that? So it doesn't have to intersect itself. So whenever there is an intersection point, like here we can see, we have an intersection point that we have there. So every time when a curve intersects itself like that, then it no longer qualifies to be called a simple curve. A curve is only simple when there is no intersection point other than there is no intersection point at all completely. You see, within this interval AB, and pay attention again here, this interval that I have here, is defined on an open interval, meaning we don't want any intersection for any of the parameter values that lie within the bounds AB. So that's what we mean when we say a curve is simple. You see. Then there are times also where we look, we study systems in which the space curve is a closed curve, like bodies that move in circles. You see that bodies that move in circles, they have trajectories that are closed. Their trajectories, they are still space curves, but now they are closed. So now let's define also what we mean by a closed space curve. You see that? So a space curve R prime of t, with t taking values that range in the closed interval a to b, is said to be closed if R prime of A is equal to R prime of B. You see that? So which means this is a curve in which the starting point coincides with the end point. Because remember, the parameter t, it always lies within an interval. So the lower end of the interval represents the starting point of the flow, while the upper end represent mostly the end point of the flow. You see that? So which means now, when the function evaluates to the same value at the end point of the interval and also the same value at the final point of the interval or the upper limit, then we say that curve is closed. You see that? So it means in this case, a particle maybe will start here and it will move, do its thing, and then it will come back to that exact location like that. So it will move, come here, go there. But at the end of the day, it will come back to the same location. So if you look at where did it start, you will still say it started here. And also where did it end, you will conclude that it ended here again. So when this is the case, that the starting point and the end point of a space curve, they coincide, then we say the curve is closed. You see that? We say the curve is closed. And if it's exactly like this, what we are seeing here, so if your curve is exactly like the one that you see here, then this is example of what we call a simple closed curve. So if a curve is closed and it doesn't intersect itself, we refer to that as a simple closed curve, like that. So yeah, those are things that you should know basically when it comes to these things that are known as space curves. You see that? But now, already we have mentioned that space curve, they are objects that at times can represent trajectories of moving objects. You see that? And every time when you have things that are moving, there are certain quantities that we start getting interest in, like if something is moving, how fast it's moving, and if something is moving, what direction is it taking as it moves. And sometimes you can even go as far as to asking things like acceleration, which is a measure of how fast it's changing its velocity of movement. And also the other things that we become interested in is calculating distances. If something started moving from here and it's still moving, we may be interested also in knowing for what is the distance that it has moved from where it started up until this point in time. So what we're going to see now is, as we move through this section, these are the things that you're going to be seeing in the discussion. But for now, the thing that we're going to just include in this section is what is attached mostly to the speed of things that are moving. You see, so we want to see now how exactly one can get to find a speed or direction of things that are moving. You see, so for example, what we want to look at now is something known as the unit tangent vector. So for people doing finance, it will be a pity now, because if you are not aware of some bit of physics, the language might be a bit challenging at this instant, because mostly space curves, they are much nicer when you discuss them in the language of physics. You see that? But you don't need to just know physics deep in general. You just have to be aware of just simple terms like velocity, how we define them in high school as the rate of change of distance, acceleration as the rate of change of velocity, and all those things. You see that? So now what we want is to introduce this object that is called the unit tangent vector. But at first, let's see and understand it before we actually get to see how one can obtain it from a space curve. You see, so let's suppose you have a space curve like this one that we have here. So you have a space curve that depicts the motion of a moving particle like that. You see. So suppose maybe the particle, at some instant you spot the particle, that this particle is here and it's moving in that direction. That's what you saw. Suppose now someone would ask you, how could you define the direction in which this particle is heading towards at this point? Or what is the direction of this particle at that particular point where it is standing right now? You see. So if you want to specify the direction of a particle at this position, there is an object that can do that for us. And this is none other than the unit tangent vector exactly at that point. You see. So a unit tangent vector, it is a vector which is tangential to the path of motion, which it is a vector which is tangential to the path of motion for that particle that is undergoing movement. You see. And this tangent vector is always denoted by T, a capital T with an arrow at the top to signify that this is a vector. And usually it's also a parameter of T, because when the particle moves and goes to that position, we have a new tangent vector which is facing in another direction. So even here again, you will have another unit tangent vector which is facing in another direction. So since this thing is a unit tangent vector, it means it has to satisfy the property that when you calculate its magnitude, it has to give you 1, like that. You see. So those are things that you should know when it comes to motion. So this object, that's the role that it plays. It plays the role of giving us the direction of that particle exactly at that position where it's located at that instant of the measurement. So that's what a unit tangent vector is. But how can you find it? You see that? Because remember, what we call a space curve, it is a function which is always described by R of t. So is there a way where we can use the description of the path of motion to actually extract this unit tangent vector? And actually there is. And how exactly is it defined? You see that? So the unit tangent vector is given by, so every time when you want to find it, this unit tangent vector, which is always in terms of a parameter, it is just given by finding the derivative of R of t, and then dividing also by the absolute value of that same derivative. So every time when you evaluate the derivative and you divide the derivative vector with its absolute value, you get what is called a unit tangent vector. You see, so that's what we call a unit tangent vector. So if you want to find it, this is the formula that you use all the time, like that. You see. So it's simple like that. So let's see some examples then, so that we can put this to practice. You see. So A typical example will be something as follows. So they will say given r of t, which is 2 sine 2t, t 2 cos 2t, where t is an element of real numbers, you see. So the question now is determine the unit tangent vector to r of t at the point root 3 pi over 6 1, like that. So this is the function that we are given. We are asked to find the unit tangent vector at this particular point. So how can we solve this problem? How can we solve this problem? So this is what we need now. So to solve this problem already, we have seen that whatever we want to find as the unit tangent vector, it is simply defined as r prime of t over the absolute value of r prime of t. So which means the only thing that we have to find is actually r prime of t. So now let's find it. So what is r prime of t in this case? So if we differentiate there, we'll see that we get 4 cos 2t, then we get 1, then we get 4 minus 4 sine 2t, like that. Easy. Now, what exactly now are we trying to find here? So we want to find the unit tangent vector at that point. But let's look exactly what this information is trying to tell us. You see, what exactly are we obtaining from here? So at this point, at the point root 3 pi over 6 1, what do we have? We have that t is equal to pi over 6. So if you look closely, you will see that at this point t has this value. Because where do we get that from? So if you look, this thing is referred to as a point. This thing that we have here is referred to as a point. But the question that you should ask yourself is exactly what is this thing? You see that? So if you are given a definition of a space curve, what exactly is it that you are given? So someone might say this is a curve. Yes, that's correct. But what is a curve when we now go fundamentally? A curve is a set of points that are joined end to end. You see that? Which means this thing, if you fix some t, this thing and this thing are actually the same thing. So which means this thing is actually this thing, but now with the parameter t being defined at some value. So the question now is, we have to now know that for this point, which is here, what was the parameter that was used to obtain it? Because every time when you have this thing here and you put some parameter value, you will always get a vector out. But what exactly is that vector? So the vector that you obtain whenever you put some parameter t is a particular point along a space curve, which means points in a space curve, they are always associated with a specific value of a parameter. So every time when a point is given in space curve, you must always be interested in knowing what parameter was used to produce it. You see. So this is the same thing that we're going to look at here. But now that is very easy. Because if you look the center term, you will see that here this center term is represented as t. Now it's represented as pi over 6. Which means this, to get this point, it is clearly seen that t must have been defined to be pi over 6. You see. So now, the fact that now we can see that it means at this case, pi is pi over 6. So which means now I can now find this derivative exactly at this point. So now what is my r prime? at this point. So now I have to find my r prime at pi over 6, and what do I get? So I'll get 4 cos. When I put pi over 6, I'll get pi over 3. Then I'll get 1. Then I'll get minus 4 sine pi over 3 again. So when I simplify this, what do I get? So what is cos pi over 3? So you can punch that in your calculator as well. Say shift pi over 3. And you get half. So you get half, which gives us 2 here, 1. And obvious, if this is half, this side has to be root 3 over 2. So it's minus 2 root 3. So this is the derivative at this point. You see that? So, and what does that mean now? So it means now what is the absolute at pi over 6? So the absolute value, which is the magnitude at pi over 6, is 2 squared plus 1 squared plus negative 2 root 3 squared, which gives us what? Which gives us root of 4 plus 1 and 12, which gives us what? 12 plus 15, which is root 17. So we can see now that from all this working that we have, we can now conclude that the unit tangent vector t of t is simply given by 1 over root 17 of 2, 1, negative 2, root 3. So that's the unit tangent vector that we are looking for. Like that. You see. So at times one example cannot do enough justice in terms of understanding what's going on here. So let's look at another example again. So in this example that we look at, this is the question. So given r of t, which is equals to 2t squared minus 1, t cubed plus 7, e to t, find the unit vector at the point 7, 15e squared, like that. So this is what we're given. Given this, find the unit tangent vector e squared. So what I'm going to do now, I will try to solve this problem as someone who is new, like to this area. So what I did in the previous problem sometimes can be confusing, so I'll try to be a lot more detailed than necessary in solving this problem, you see. So that at least you can get it once and for all, and in terms of how exactly should you solve this problem. So every time when this problem is posed, you will always be given your RT function and some particular point. So what I'm going to do now is we'll just try to put some recipe as to how exactly do you find the unit tangent vector. So every time when you want to find a specific unit tangent vector, the first thing is you differentiate the given space curve. And when you differentiate that, you'll get 4t. And then when you differentiate that, you'll get t cubed. Sorry. You will get 3t squared. And then we'll get e to t in the other case. Then the next thing that you have to do now is, for this point that is given, what parameter was used to obtain it? So every time when you want to find the t value that was used to produce a specific point, what you do is you can equate this given point to the general point RT. You see that? So you can come and say if 2t squared minus 1 t cubed plus 7 e3 is equals to the given point 7, 15 e squared, then what? If these things are equal, then what? So we know that two coordinates can only be equal if they are equal component wise. So it means 2t squared minus 1 must equal to 7, and t cubed plus 7 must equal to 15, and e to t must equal to e squared. You see. So then the next thing that you have to do is you can solve these equations, all of them, but the expectation is that all these equations must give you the same solution. But let's see that if that is going to hold true. You see that? So let's try the first equation. So now, from 2t squared minus 1, we get 2t squared is equals to 8. So t squared is equals to 4. Therefore, we can see that t is equals to 2 here at this instant. You see that? So, and also here you can see that t cubed is equals to 15 minus 7, which is equal to 8. So when you cube root both sides, and you cube root here, you still get that t is equals to 2. Then here, the other side, you can see simply that t is 2 because bases are the same. So once you have established what parameter was used, then now the next thing is to evaluate your derivative at that parameter. So now what we calculate is what is r prime of 2. So r prime of 2 is 8, 12 e squared, like that. Then the next thing, we can now find what is the absolute value of r prime 2, which is going to be root of 8 squared plus 12 squared plus e squared squared, and which gives us what? 64 plus 144 plus e4, which gives us root of what? So 64 plus 144 is equals to 208 plus e4. So therefore, what is the tangent vector? So therefore, the unit tangent vector is t, which is equals to 1 over root of 208 plus e4 times the vector 8, 12 e squared. So this is your unit tangent vector that you'll be looking for. So yeah, that's it. So every time when they say find a unit tangent vector, then that's all that you have to do. Then you're done, you see. So these are things that you should practice and make sure that you know how to get them all the time when they are needed, you see. And also don't forget the physical meaning behind these. So this thing is always a tangential vector to that point of interest, you see. So like, for example, if we were to illustrate here where exactly this thing lies. So if I have a Cartesian plane, something like this, and then I come here maybe and I draw my curve, then how can I actually represent this unit tangent vector? So the unit tangent vector, to represent it, it will be as follows. So if I come here and draw my r of t to sit here, it means the unit tangent vector now will be that vector which is tangential going there. That's what it is. So now this point here will be that specified point. Like for example, now what point was given? It was the point 715 e squared. So you come and say 715 e squared. So this is the unit tangent vector that you are referring to, like that. So those are things that you must make sure that you understand pretty well when it comes to this section, how to find the unit tangent vector at a specified point. Then the next thing that we want is the equation of the tangent line. You see, how do you find the equation of the tangent line? How do you find the equation of the tangent line? So a tangent vector and the equation of tangent line are different. You see that? So let's try to understand in what way are they different. So x, y, z. So let's draw maybe a typical space curve in this region. So it's going like that. And then let's fixate ourselves maybe at this particular point, so that we can understand what is the difference between a unit tangent vector. So a unit tangent vector is a small vector which is tangential to the curve and has a length of 1 unit. So it's a very small vector such that its length is just 1 unit. You see that? But what about a tangent line? So what is a tangent line at that particular point? So a tangent line at that particular point is something like this. It is a line which goes along that very tangent vector. So it is a line that goes along there. You see? So in such a way that the direction of the line is exactly parallel to the unit tangent vector. But the line now is something that goes from infinite end to the other infinite end. So this is what we mean when we talk about a tangent line. So this is a tangent line. So there is a tangent vector and a tangent line, and this diagram actually shows the distinction between these two. So a tangent line is a line that moves throughout the whole space and is tangential to the curve at that particular point, while the tangent vector is just a very small vector of 1 unit at that tangent point. You see. So there are some questions where you can actually be asked to find the equation of the tangent line. So what I'm going to do now is I'm going to give you the formula for how exactly do you find the equation of the tangent line, and you're just going to be using it all the time to find the equation. So I'm not going to do an example because it will be simple and straightforward, because it's a matter of just plugging in the information that is given. So what is the equation of the tangent line? So the equation of the tangent line is given by, so every time when we want to find the equation of the tangent line, it is given by r prime of tau is equal to a plus tau t. You see? So that's what it is. So let's understand. So what is tau? Tau is just some parameter, which means you can call it anything. So which means you can just call tau maybe to be s, mu, even t itself, no problem with that. Though I'll try to use something different, and etc. like that. So this is quite obvious. But what is this thing sitting here? So this object sitting here is none other than the unit tangent vector. So this is simply the unit tangent vector. So this question is usually asked after already you have calculated the unit tangent vector. So you just multiply it by that. And then what about this? So this is actually the given point. This is actually the given point, like that. So that point that is given, now you just write it as a vector, and then you're done, like that. So that's how things work here. It's very simple and straightforward. So it's not something that is very much complex to do. Though maybe someone might say, okay, let's just see an example on how exactly do we do it. So let's just do a small example on how exactly can we do it. So a typical example will be given r of t, which is equal to t squared minus 1, then t cubed plus 7, and t4, determine the equation of the tangent line at the point zero, 8, 1. You see, So you can be given this, given r of t equal to that, determine the equation of the tangent line at this particular point. So how will we solve for that? So to solve for that, we proceed as follows. So we know already that the equation that we're trying to look for, we know that it has to have this form ra plus some tau of t. So which means we have to find the unit tangent vector because the point is already given. You see? So now what is A? So A is the given point. So if you take that point, which is 0, 8, 1, write it as a vector, that's your point. Tau is tau, so we have to find T. So now, what is R prime of T? So R prime of T, we differentiate that. So we get 2T, 3T squared, and 4T cubed. Then now we have to see this point that is given, what parameter value corresponds to it. So to find that, we can equate the points. You see, so we can say if what is given, which is t squared minus 1, t cubed plus 7, and t to 4 is equal to 081, then what? So you can equate any two components of your choice. So I see already t4 is 1, which follows that t should be 1 at this instant. You can see also if t is 1, all the other two components, they come out the same as what we see. So this has to be the t value that was used to produce that point. So now knowing it, what follows from that? So we have r prime of 1, which is 2, 3, 4. Then we divide, find the modulus. R prime of 1 is 2 squared plus 3 squared plus 4 squared, which gives us what? So we have 4 plus 9 plus 16, so which is root 29, like that. So knowing this, now what is our unit tangent vector? So this implies our unit tangent vector t is just 1 over root 29, then by 2, 3, 4. So therefore, what is the equation of the tangent line? So therefore, equation of the tangent line is what? It's r of tau equal to a, where a already we say the point given, which is 081. So it's going to be 081 plus tau times t, so it's tau over root 29 and 2, 3, 4. You see, so that's your tangent line. So once you get this, this is the equation of the tangent line that is required. But sometimes they can go further than this. They can say, determine the parametric equations of the tangent line. So how can you get then the parametric equation of the tangent line? So if you want then to find the parametric equation, this is how you proceed. So from here, what follows is the right-hand side can be compressed. You see, so this can be compressed to a single vector by adding component-wise. So you will get 2 tau over root 29, and you will have 8 plus 3 tau over root 29, and 1 plus 4 tau over root 29, like this. Then the next thing that you should recall is what exactly is this thing. You see, so r of tau just represent x of tau, y of tau, z of tau. So that's what this thing stands for. So which implies, in this case, x of tau, which is x, is just simple 2 over root 29 tau. And what about y? Y in this case is 8 plus 3 over root 29 tau. And what is z? It's 1 plus 4 over root 29 tau. So these are what we call the parametric equations of the tangent line. You see, so what we just obtained here are what we call the parametric equations. of the tangent line. So yeah, that's it. So we're gonna just pause it here today, and then we are going to continue more and more things about the tangent, about the parameter space curve in our next lesson. Otherwise, thanks for watching, guys. See you when I see you. Bye.